Chapter 1, Gas Laws. Now, we learned about the three states of matter in Form 1 and the arrangement of particles in each of the states. Most substances can exist in any of three states, depending on temperature and pressure as well. In this chapter, we shall focus on the behavior of gases when subjected to various conditions. We said that particles in gases have weak intermolecular forces and are therefore far apart, moving randomly in all directions. Therefore, gases will often fill any container in which they are put. Because the particles are far apart, gases can be made to occupy a lesser volume by applying a force. We say gases are compressible. And from this word press, we get pressure. What is pressure? Now, you might have learnt elsewhere that pressure is the force acting on an object per unit area. Consider this box weighing 10 newtons resting on a table. That box exerts pressure on the table because of its weight and the area in contact with the table. Pressure is equal to force over area. 10 newtons divided by 1 times 2 the area of the box in contact with the table, which gives us 5 newtons per meter squared. How about pressure in gases? When gases are confined in a container, their particles move around, colliding with one another and with the walls of the container. By colliding with the walls of the container, the particles exert pressure on this container. Remember, gases too have weight. When we press down the piston, we increase the pressure. Why? Because by reducing the volume, we increase the number of collisions per second between the particles and the walls of the container. From our calculation, we gave the unit of pressure as newtons per meter squared, derived from the units of force or weight and area. Newtons per meter squared is also called Pascal. So 1 newton per meter squared is equal to 1 Pascal. Another unit of measuring pressure is atmospheres. 1 atmosphere is equal to 101,325 Pascal. Pressure can also be measured in millimeters of mercury. When a mercury barometer is placed at sea level, the mercury column rises up to 760 millimeters. The atmospheric pressure at sea level is therefore 760 millimeters of mercury, which is equivalent to 1 atmosphere. Let's talk about gas laws. Now, there are 3 variables that are manipulated in the different gas laws: pressure, temperature, and volume. To see how one variable affects the other, we have to hold the third variable constant. Boyle's law. Boyle's law deals with the relationship between pressure and volume of a gas at constant temperature. If you exert pressure on a gas, you compress it, and that means it takes less space. Imagine a hard container that measures how many times gas particles bang against its walls. The more the gas particles bang against the sides, the higher the gas pressure on the container. If you make the container smaller, you compress the gas. The gas particles will hit the walls more times per second, so that means higher pressure. If you keep the number of gas particles constant but make the size of the container bigger, there will be fewer collisions per second, and that means lower pressure. So as you can see, for a gas, pressure and volume are inversely proportional. If you keep everything else constant, then as the pressure on a gas goes up, its volume goes down. As the volume goes up, the pressure goes down. A British scientist, Robert Boyle, stated this inverse relationship between pressure and volume as a gas law. Boyle's law states that for a fixed mass of a gas at constant temperature, pressure and volume are inversely proportional. Mathematically, P is proportional to 1 over V. Introducing a constant, P is equal to K over V, where P is pressure, V is volume, and K is a constant of proportionality. We can rearrange this equation to read PV is equal to K, or the product of pressure and volume is a constant. Often, Boyle's law is used to compare two situations, a before and an after. In this case, we can say P1V1 is equal to K and P2V2 is equal to K as well. Because both are equal to K, then it means they are equal to each other. So we can have P1V1 is equal to P2V2. This is the mathematical expression of Boyle's law. Let's take an example. A tire with a volume of 11.5 liters reads 304 kilopascal on the tire gauge. What will be the new pressure if the tire is compressed to a volume of 10.6 liters? We write Boyle's law and substitute what we know. This is a before and after situation. P1V1 is equal to P2V2. 304 kilopascal times 11.5 liters is equal to P2 times 10.6 liters. To solve for P, we divide both sides by 10.6 liters. 10.6 liters cancel out. Liters cancel out here. 304 kilopascal times 11.5 over 10.6 is equal to P2. 329.8 kilopascal is equal to P2, which is the same as P2 is equal to 329.8 kilopascal. Another example. A syringe has a volume of 12 cubic centimeters and a pressure of 1.4 atmospheres. If the end is plugged so that no gas escapes and the plunger is pushed down, what must the final volume be to change the pressure to 3.6 atmospheres? P1V1 is equal to P2V2. 1.4 atmospheres times 12 cubic centimeters is equal to 3.6 atmospheres times V2. To get V2, we divide both sides by 3.6 atmospheres. 3.6 atmospheres cancel out, and atmospheres cancel out here. We remain with 1.4 times 12 cubic centimeters over 3.6 is equal to V2. That gives us 4.666 cubic centimeters is equal to V2, which also means V2 is equal to 4.666 cubic centimeters. Now, the values are given in two significant figures, so we give the same kind of an answer. V2 is equal to 4.7 cubic centimeters. Next law, Charles' law. Now, Charles' law deals with the relationship between volume and temperature at constant pressure. If you heat a gas, it expands, making them to move faster and therefore take more space. Imagine a balloon that expands when gas particles bang against the sides. By expanding, that keeps the pressure constant. The faster the particles move, the more they push against the balloon, expanding it. If on the other hand you cool the balloon down by putting it on ice, that slows down the gas particles and the balloon contracts. So for a gas, the temperature and volume are directly proportional. Keeping everything else constant, as the temperature of a gas goes up, its volume goes up as well. As the temperature goes down, its volume goes down too. A French scientist, Jacques Charles, stated the relationship between temperature and volume of a gas as a law. Charles' law states that the volume of a fixed mass of a gas is directly proportional to temperature if the pressure is constant. Mathematically, V is proportional to T. Introducing a proportionality constant, we shall have V is equal to KT, where V is volume, T is temperature in Kelvin, and K is the constant of proportionality. We can rearrange this equation to read V over T is equal to K, or the ratio of volume and temperature is a constant. Equally, Charles' law is often used to compare a before and an after situations. So we can say V1 over T1 is equal to K and V2 over T2 is equal to K. Having K in both situations, we can therefore say V1 over T1 is equal to V2 over T2. And this is the mathematical expression of Charles' law. Let's take an example. A hot air balloon has a volume of 3,000 cubic meters at 100 degrees Celsius. What will be the volume if the temperature cools to 80 degrees Celsius? First, we write the Charles' law. V1 over T1 is equal to V2 over T2. We substitute in what we know. Remember to convert temperature to Kelvin by adding 273. So T1 is equal to 373 Kelvin and T2 is equal to 353 Kelvin. 3,000 cubic meters over 373 Kelvin is equal to V2 over 353 Kelvin. Solve for V2. To remain with V2 on one side, we multiply each side by 353 Kelvin. 353 Kelvin cancels out here, and Kelvin cancels out here. So we shall have 353 times 3,000 cubic meters over 373 is equal to V2. V2 is equal to 2,839 cubic meters. One more example. At 0 degrees Celsius, a gas occupies 22.4 liters. How hot must the gas be in Celsius to reach a volume of 25.0 liters? V1 over T1 is equal to V2 over T2. Convert the temperature to Kelvin. T1 is equal to 273 Kelvin. 22.4 liters over 273 Kelvin is equal to 25.0 liters over T2. Solve for T2. For us to solve for T2, we need to cross multiply here. T2 times 22.4 liters is equal to 273 Kelvin times 25.0 liters. To get T2, we divide both sides by 22.4 liters. 22.4 liters cancels out here. Liters cancel out here. So T2 is equal to 273 Kelvin times 25.0 over 22.4. T2 is equal to 304.7 Kelvin. We convert back to degrees Celsius by subtracting 273, and T2 is equal to 31.7 degrees Celsius. Next, we look at the combined gas law. Now, Boyle's and Charles' laws are concerned with the volume of a fixed mass of a gas and how that volume changes with variations in temperature and pressure. In each case, one variable is kept constant with the other two allowed to change. But often in the natural environment, all variables tend to change and the two laws only apply in experimental cases. What happens if we have all variables changing? We use a combined equation. This is the expression of Boyle's law, and this is the expression for Charles' law. If we combine them, then we have a combined gas equation. PV over T is equal to K. If we have a before and after situations, then we shall have P1V1 over T1 is equal to P2V2 over T2. If you hold any of these variables constant, then you can derive the other basic gas laws. If you hold pressure constant, then you have Charles' law. If you hold temperature constant, you have Boyle's law. What if you hold volume constant? Well, you get another law called Gay-Lussac's law, which is not part of our syllabus. So the combined gas equation can be used to solve any question relating to gas laws. If you can't remember the other gas laws, simply use the combined gas law. Let's take an example. A gas occupies a volume of 0.12 liters at 50 degrees Celsius and a pressure of 110,000 Pascal. At what temperature would the same mass of the gas occupy 0.10 liters under a pressure of 125,000 Pascal? This is a before and after situation. We write the combined gas equation. P1V1 over T1 is equal to P2V2 over T2. Then we substitute in what we know and remember to convert temperature into Kelvin. 50 degrees Celsius is equal to 323 Kelvin. 110,000 Pascal times 0.12 liters over 323 Kelvin is equal to 125,000 Pascal times 0.10 liters over T2. Solve for T2. We do cross multiplication. T2 times 110,000 Pascal times 0.12 liters is equal to 323 Kelvin times 125,000 Pascal times 0.10 liters. To get T2, we divide both sides by 110,000 Pascal times 0.12 liters. All these cancel out and the units cancel out as well here. So T2 is equal to 305.9 Kelvin. We give our answer in degrees Celsius, so we subtract 273, and that leaves us with 32.9 degrees Celsius. Next, we look at diffusion. Now, we already know that gas particles are spread out and move randomly in all directions. And this explains why gases take the shape of the container in which they are put. It is because the gas particles will continue to travel in a straight line until they hit something, in this case, the walls of the container. So the smelly gases given by rotting vegetables in a sealed box will fill the box with the rotting vegetable smell, but you won't be able to smell them outside the box. But if the lid is taken off, the particles will no longer be contained, but will escape into the air around the box, and you will soon feel the effect. These particles are reaching your nose by diffusion. Diffusion is the net movement of particles from a region of high concentration to a region of low concentration. It is a process that doesn't rely on wind or air currents. it will happen even in still air. So why does the smell take some time to be felt on the other end? Just like the gas particles collide with the walls of the containers, they also collide with each other and with other particles in the air. This slows them down, and this collision is always taking place. And therefore, if all gases diffuse, the next question is, do all gases diffuse at the same rate? To answer that question, let's perform an experiment. We take a solution of ammonia and a solution of hydrochloric acid. We take a cotton ball and dip it in the ammonia solution and another in the hydrochloric acid. We place the two cotton balls in a glass tube at the two ends simultaneously and close the two ends with rubber corks. Ammonia solution will release ammonia gas and hydrochloric acid will release hydrogen chloride, which will begin to move in the opposite direction. After some time, the two gases will meet and react to form white solid of ammonium chloride. Note the point where the gases meet. Obviously, ammonia traveled longer than hydrogen chloride, and this means ammonia diffuses faster than hydrogen chloride. So the answer to our question is no. Different gases diffuse at different rates. In 1883, a British chemist, Thomas Graham, investigated the relationship between diffusion rates and densities of gases, and he came up with what we today call the Graham's law of diffusion. It states, the rate of diffusion of a gas is inversely proportional to the square root of density at constant temperature and pressure. Mathematically, rate is proportional to 1 over the square root of density. Introducing a constant, we have R is equal to K over root D. Rearranging that, we shall have R times root D is equal to K, where R is the rate of diffusion, D is density of the gas, and K is a constant of proportionality. K is uniform for all gases. So, if you have two different gases, A and B, Ra times root dA is equal to K, and Rb times root dB is equal to K as well. And that means Ra root dA is equal to Rb root dB. If we rearrange this to have rates on one side, we shall have rate A over rate B is equal to root dB over root dA. Or you can put the densities under one square root. Rate A over rate B is equal to the square root of density B over density A. Remember, density is equal to mass over volume. And considering the gases being compared have the same volume, we can use mass in place of density. So we shall have rate A over rate B is equal to the square root of mass B over mass A. The mass we are talking about is the molecular mass. So let's compare the rates of diffusion of ammonia and hydrogen chloride. The molecular mass of ammonia is given by 14 for nitrogen plus 3 times 1 for hydrogens. That gives us 17. Molecular mass of hydrogen chloride is equal to 36.5. So rate for ammonia over the rate for hydrogen chloride is equal to the square root of 36.5 over 17. And that gives us the square root of 2.148. And that is equal to 1.47. It's a ratio of two rates, so it's unitless. It therefore means that ammonia diffuses 1.47 times faster than hydrogen chloride. If we look at our experiment, ammonia traveled 30 centimeters while hydrogen chloride traveled 20 centimeters. 30 over 20 is equal to 1.5. So you can see our experimental value 1.5 is not very far from the calculated true value. And therefore, according to Graham's law, the denser the gas, the slower its diffusion rate, much like a light boy would outrun a huge overweight man. Now, when we talk about rates of diffusion, the only experimental variable that we can measure is time. How much time does a given gas take to diffuse? So we need a relationship involving time. Rate and time are inversely proportional. That is to say, if a gas diffuses at a higher or faster rate, then it takes less time. If it diffuses at a slower rate, then it takes more time. Mathematically, rate A over rate B is equal to time B over time A. This is Graham's law. Rate A over rate B is equal to the square root of mass B over mass A. Looking at these two expressions, we can replace rate A over rate B in the Graham's law with time B over time A. So we shall have time B over time A is equal to the square root of mass B over mass A. In short, time is directly proportional to mass. The denser the gas, the longer it takes to diffuse. Let's take an example. An unknown gas A takes 112 seconds to diffuse through a tube. An equal volume of oxygen at the same temperature and pressure takes 60 seconds to diffuse through the same tube. Given that the molecular mass of oxygen is 32, calculate the molecular mass of gas A. So we have time and mass. Our expression, time A over time B, is equal to the square root of mass A over mass B. So 112 seconds over 60 seconds is equal to the square root of mass A over 32. Let's separate the square roots so that we can be able to work. 112 seconds over 60 seconds is equal to root MA over root 32. We cross multiply. 112 times root 32 is equal to 60 times root MA. We divide both sides by 60 to remain with root MA. So 60 seconds cancel out. So we remain with 10.56 is equal to root MA. To get MA, we square both sides. And MA is equal to 111.5.